Hey everyone, let's talk about the idea of phase velocity versus group velocity. Now I've written down the solution to the electric field profile in a parallel plate waveguide under transverse electric polarization. So let's go ahead and just kind of draw that now. So here's a waveguide, parallel plate, like so. So here is PEC, perfect electrical conductor, up here. And again, there's PEC down here, perfect electrical conductor. And we are separated by that usual distance d, and this is the z direction. So looking at this little expression here and kind of plotting some of the solutions, you remember if you watch some of the little demo videos, you would see these little blobs of energy. So if this is like the n equals 1 mode, you would see kind of a positive peak, negative, positive, negative, and those blobs of energy would propagate down the waveguide with some apparent velocity. Well, it turns out this term here can be used to kind of indirectly calculate that apparent phase velocity down the waveguide. And it's a pretty straightforward calculation where you would say beta sub n is equal to omega divided by Vp, comma n. Right, so this is in the same sense that the free space wave number is omega over c for a plane wave propagating in free space. I have this sort of longitudinal propagation constant, which would satisfy the same thing. Right? And this mathematically follows out kind of just the definition of all this stuff, acting as a cosine term with a omega t dependence in the time domain. So what this sort of implies is Vp sub n is equal to omega divided by beta sub n, that propagation constant. Now everything seems all on the up and up, except something interesting happens. You'll notice beta sub n is actually less than k naught. And in fact, as I step up my transverse wave number here, I get closer and closer to 0, in fact, until you eventually reach cutoff where this is in fact 0. So that means for larger and larger n, this phase velocity gets bigger and bigger, which remember, the speed of light is omega over k naught, and this phase velocity is omega over this beta. And you compare the two, this beta is less than this k, just by that looking at that difference. So that means we get the phase velocity on some mode propagating down a waveguide can in fact be greater than the speed of light in a vacuum. So you see that the mathematics fell out of Maxwell's equations, and yet something is amiss here. How does my phase velocity exceed the speed of light? Doesn't that violate relativity? What's going on here? Something is amiss. So the answer, it turns out, is nothing is amiss. This is actually a real thing, and you can even see it for yourself. If you watch some of the video demos where I animate the fields as they propagate down, they actually start propagating faster and faster as you increase the propagation constant here, the mode number. And because I'm stepping them in equal time steps for each frame of the animation. So you can compare them side by side, and yes, as they go higher, they'll go faster. But you got to remember what physically is happening inside this waveguide. So we did an exercise in class where we broke down this sine term basically as a superposition between two waves. So you have one wave vector kind of going up, and then another wave vector going down, and those two waves are superimposing onto each other. And so as you go higher and higher in wave number, you kind of imagine those two vectors stepping up like this, where the hypotenuse is the same length, but its y component is getting higher and higher, and then the longitudinal bit gets shrunk more and more. But the hypotenuse has to stay the same length. So why is that significant? Because you imagine, let's say I'm going to tag this little point here where the two waves are, say, constructively interfering. So it's a peak in my signal. Right, that little point, the top of the wave crest, appears to be moving in that direction. But that motion of that peak is technically an illusion. So a great analogy to this is to imagine, say, a beach. Okay, so here is a beach, and this is ocean out here. And now just imagine a wave striking the beach at some angle like this. And I ask, what is the intersection between the crest of the wave and the beach? And I imagine asking myself, how fast is that little intersection point propagating to the right as this wave kind of comes in and strikes the beach here? Like so. So that's an arrow. So think of that as a wave vector for an ocean wave. So you can see as this angle approaches 90 degrees, that little point will appear to swoosh along the beach very, very quickly. But it's not really a physical thing. It's sort of a geometric point that's defined by the intersection of other real things. The thing that's moving is the wave here, and that little point is just kind of, it's a point I can define and describe mathematically, but it's not a real thing that moves and carries real information. So this phase velocity here in a waveguide is technically a fiction because it's the result of these two waves overlapping in each other, and they have regions of constructive and destructive interference, and the peaks of those phases aren't really things that carry information. They can appear to move with a very large phase velocity, even though it's very analogous to this situation here. So the way you can kind of approach this question a little bit differently is to ask yourself, what would happen if I were to excite this system with a constant sinusoidal signal? And then eventually the energy would fill in the waveguide and you would see all the propagation of the waves. And then I perturb this a little bit. Maybe I increase the amplitude a little bit and then I turn it back down again. And then you ask yourself, how quickly will that perturbation make its way down the waveguide? And it turns out the velocity of propagation for that little perturbation is not going to follow the actual apparent phase velocity here. So that implies if I perturb a little bit, that perturbation will still obey relativity because it is something that carries real physical information, whereas this little phase here does not. So let's ask ourselves another question. How do I calculate the propagation of information in that little perturbation? So there's a word for that in electromagnetic field theory. It is called the group velocity. So I'm going to denote this V sub g, the group velocity. So we're going to derive the group velocity for a parallel plate waveguide. And the proof for this is kind of ingenious. It's a little esoteric in that you got to do a little bit of a Fourier transform and linear system theory, but it's a pretty straightforward proof and it's kind of brilliant once you see it. So we're going to walk through it step by step now. So what we're going to do is imagine a black box, something kind of like this. And I'm going to have like a wire here with a signal, S sub I of t. So that's my input signal. It's going to go through this magical black box, then out at the other end will pop my output signal. So I have an input signal and an output signal. And in here is an impulse response function. So we're doing some kind of linear system theory here, right? And of course, that implies the Fourier transform, which is a transfer function, h of omega. So all I'm going to assume is the following. H of omega is equal to some constant, we'll just call it h naught, some constant of proportionality, e to the minus j beta z. At least your book uses z. I think it might make a little bit more sense to say h naught e to the minus j beta L, but some fixed length. So imagine a length of transmission line here, say, or it could be some length of my parallel plate waveguide. And if I excite it with a sinusoidal steady state signal at some single frequency, then the output at the other end will just be this phase shifted thing here, which is proportional to this constant multiplied by the distance through which it has traveled. That's what this is basically saying. So remember, however, this propagation constant is not exactly a constant at all. In reality, in fact, beta is a function of omega. So it's not constant. It will change depending on my frequency of excitation, which we can see right here in this relationship. So we'll write this out now. We'll say beta of omega for some particular waveguide mode is going to be the square root of omega over c naught squared minus gamma sub n squared. So that's for, say, the nth mode here. So you notice it's a function of omega. If I change the frequency, I will change this propagation constant and thus change this behavior up here. So this is the expression for a waveguide, but depending on the system, it could be something else entirely. It could hypothetically be a quantum mechanical wave obeying some dispersion relation here. Any sort of wavy system, ocean waves, will have their own dispersion relation related to this as well. So this idea is very important. This thing is not really constant with frequency. So what's the next step? Next, I'm going to assume a particular form for this signal. I'm going to assume something like this. S sub I of t is equal to f of t times cosine of omega naught t. Or I could say sine omega naught t. It doesn't really matter. But you notice I have a carrier wave here, and then a modulation function. Like that. So that's the modulation, and that's the carrier here. All right? So very simple. And we're going to assume this is kind of a very narrow band modulation, so that I'm just slightly perturbing this thing a little bit at the input. So I have a constant signal here with this little tiny bit of a perturbation on top of it. Given this information alone, can we calculate the group velocity? And the answer is, it turns out, we can. There's a mathematical derivation for this. So first things first. From linear system theory, we know that S out of t is going to be S I of t convolved with the impulse response h of t. That's just how linear system theory works. And we're going to take the Fourier transform of this. So what you will then get is something like the following. S out of omega. So that's a capital S, so I'm going to do something like that. So we've taken the Fourier transform of everything. And remember, convolution in time domain means multiplication in the frequency domain. So I get Si of t multiplied by h of omega. So we know what that is because we already assumed it here. It's just some propagation delay due to some fixed amount of length in that little system here. What is this guy here? Well, you notice I have multiplication in the time domain implies convolution in the frequency domain. So we're just going to write this out maybe over here on the side. Let's see. We'll do it here. So let's come up here. S sub I of, oh, sorry, that should be an omega, excuse me. So put an omega there, not a t. So capital S of omega, omega, omega. So S of omega is going to be the convolution of these two guys. So it's f of omega, so it's the Fourier transform of that, convolved with the Fourier transform of that, which is simply delta of omega minus omega naught. So when you convolve with a delta function, this is the sifting property, I will get simply f of omega minus omega naught. So let's just kind of draw that out for a second. So here we go. Let's draw some axes. So here's my omega here, my omega axis. Here's some omega naught. And I might have some little bit of spectrum here doing that. That is my f of omega, which is time shift or frequency shifted around the carrier. So this is what happens when you modulate any sort of carrier wave. You just have the Fourier transform of your modulation. It's shifted over here and centered about your signal here. So you'd call this, well, let's redraw this. So I have the magnitude of f is what I'm plotting here, and this guy here is simply f of omega minus omega naught. Let's call this the magnitude of Si of omega. So that's my input signal. I'm in the frequency domain. That's my modulation function here, my modulation spectrum, we'll say, and it's centered at the carrier. So what happens now? Well, all that means is I have my output signal as a function of omega is going to satisfy, I'm just going to plug in these definitions. So I'm going to plug in this definition here and this guy over here for my product. So we will get the following: H naught f of omega minus omega naught times e to the minus j beta of omega times my length, z. All right, so now all I have to do is take the inverse Fourier transform of that, and that will give me S out of t. So again, that's a little s, that's a big S there. So little s in time, big S in frequency. So what does that look like? Well, this is kind of messy, so this is going to get a little rough. So try and follow along here and keep up. We get S out of t is going to be 1 over 2 pi times the integral from minus infinity to plus infinity of this whole thing here. H naught f of omega minus omega naught e to the minus j beta z. So that, just remember, that's a function of omega here. And there will be an e to the j omega t d omega. That is the inverse Fourier transform. And if you read the book, they also slap on taking the real part of this so that I get a real valued signal in my time domain. But that's kind of a mathematical bookkeeping we won't really worry about too much. So just kind of keep that in the back of your head there. So this is a monster. Okay, you look at that. How do I take the inverse Fourier transform of this big, horrible integral here? So what we're going to do, we're going to make another quick little assumption. F of omega is narrow banded. Right? So the idea that it's just a slight little perturbation, a slight little modulation on top of my carrier. Okay, so I may have exaggerated a bit. Maybe in reality it's just kind of a little, tiny little thing like that. Maybe I've overdrawn it. It doesn't matter. So narrow banded just means the bandwidth on this thing is relatively small. So what this will imply is the following. I have my beta as a function of omega. I'm going to take the Taylor series expansion of this. And what you'll get is beta of omega naught. So I'm doing the Taylor series about omega naught here. Plus omega minus omega naught times beta prime. So that's the derivative with respect to omega evaluated at omega naught. And of course, there's going to be a bunch of other terms here, but I don't care about them. When you are narrow banded, all those terms out there are going to become imperceptibly small, and so we don't care about them. Okay, so I'm only going to look at the first two terms in this Taylor series expansion. And you just then plug all of this stuff here, right here. That gets plugged in for this beta here. So it's going to be a little ugly, so just bear with me for a few more moments. And we'll get 1 over 2 pi, some little real bit here just for completeness. H naught f of omega minus omega naught. Now we're going to, I got this e to the j omega t, and now I'm going to get this nasty thing up here, e to the minus j. So just for notational sake, I'm going to give this guy a name. I'm going to call this thing here, let's call that beta naught. Okay, and then this is going to be beta naught prime. So it's beta evaluated at omega naught, the carrier frequency, and the derivative evaluated at that. So what you will get is e to the j beta naught z, and then I'll have a e to the minus j, and then there'll be an omega minus omega naught beta prime naught times z d omega. Okay, so this is actually tractable. It doesn't look like much, but you can calculate this. It's a little nasty, but you notice I have a bunch of products in the frequency domain. which is going to turn into convolution in the time domain, which you can imagine, these are going to turn into some delta functions on top of delta functions. And there is a solution. The book kind of shows you a little bit of, change of variables, rearrange some terms. It's not pretty. It's a pretty yucky little derivation. But the answer is actually pretty simple. So we're just going to pretend we're not going to waste too much time on the details. It is nasty, but it has a solution. And it will look like the following. S naught of t is equal to f of t minus, get out my notes, there we go, beta naught prime z times cosine omega naught t minus beta naught z, like that. So I had an input signal. So just for reference, I'm going to write my input signal off to the side here. So remember, S sub I of t was f of t cosine omega naught t. So that was my input, and then I ran it through this little delayed system, and this is what came out at the other end. And all I did was just some Fourier transforms on it. By definition, I have a system where, so let's see if I can get that. So here was my system. I have an input signal, and all I did was add some delay, some little for each frequency, and each little frequency had its own little delay there, and then this thing would pop out. So it just straight up Fourier transforms, and this thing pops out. Okay, so now when you look at this, some interesting things start to happen. First off, this guy here looks pretty normal, right? Remember when you define a traveling wave in these terms. So let's kind of do something like this. I'm going to look at just this guy here. This implied my phase velocity was equal to omega over beta naught. So that thing didn't really change. It still has its little phase velocity, but this thing over here seems a little bit different, doesn't it? So I'm going to define this little term here. I'm going to call that t sub 0, okay? So that for this little guy. So you notice I have this t minus t naught. So there's a time delay on my modulation, in effect, this sort of equivalent time delay associated with propagating down that little line here. So remember, distance is rate times time, or velocity times time. So that means time is going to be, t naught is going to be distance divided by velocity. So z over velocity, I'm going to call that v sub g, which was, if we look at our notes here, I'm going to get beta naught prime z. So this is the definition of what that time delay should entail, right? There's a change in distance divided by a velocity implying a time, and the time delay satisfied this little expression here. So you do a little bit of jiggering here, rearrange, and what you find is the group velocity, so the velocity, the perturbation of my, or the velocity of my perturbation, my modulation, is going to be 1 over beta naught prime. Okay, so the group velocity follows this other little relation. So remember, beta naught prime is equal to the partial derivative of my propagation constant with respect to beta evaluated at some particular frequency here. Okay, or we can just simply write that as beta naught prime of omega naught. Okay, so it's 1 over that thing. Okay, and that's the group velocity down any sort of system with a delay. And so it's not the same as the phase velocity. Isn't that interesting? So let's do a quick calculation on this to see what it evaluates to. So remember, where'd my notes go? There we go. So remember, the nth mode, beta sub n, is equal to the following. I'm going to have a k naught squared minus gamma sub n squared, square root of that, which is equal to omega over c naught squared minus, I'll just leave this at gamma n squared. That's a constant. Okay, so I am now, so remember, this is a function of omega. So let's write it out explicitly. Beta sub n as a function of that frequency. So let's take its derivative. So partial beta n with respect to omega is going to be 1/2 times 2 over C naught. Sorry, 2, excuse me, I missed a term. 2 omega over C naught. So that's the derivative of the inside. So the radical comes down to the 1/2, and I do the derivative of the inside here, and then I'm going to get omega over C naught squared minus gamma sub n squared to the negative 1/2. So that's just the derivative of this guy here. So let's just rewrite that really quick. So the 1/2s go away. So I'll have omega over C naught divided by the square root of omega over C naught squared minus gamma sub n squared. So you notice the denominator here is just my original term here. So I'm going to get omega over C naught divided by beta sub n. And if we evaluate this at omega naught specifically, so remember we care about what is my group velocity at a particular frequency. So what I'm going to get is essentially beta prime sub n evaluated at omega naught is equal to omega naught over C naught divided by beta sub n at omega naught. So the inverse of that, the group velocity, is 1 over that, 1 over beta naught prime. So we'll just invert that. So let's see, I'm going to cross that out and put a C naught there. And I'm basically going to get the following. Beta naught C naught, so that's beta, over omega naught. Like so. So, isn't that interesting? Remember, K naught is equal to omega over C naught, so my free space wave number. So what this implies is I get the following, beta naught over K naught, which is always going to be less than or equal to the speed of light. Okay, so there we go. So we've shown that the group velocity is going to satisfy special relativity. We're not going to create faster than light travel with this. We are still limited by the speed of light. And so you can see at the end of the day what that fundamentally means. So I have a waveguide, I've excited it with some particular continuous frequency, and if I modulate it just a tiny bit, I turn up the amplitude and I turn it down, or maybe I turn it on and I turn it off, and every single mode is going to have some corresponding group velocity associated with it. And that little perturbation will very gradually make its way down the waveguide, but that perturbation will not exceed the speed of light. And what's interesting, you can also see that as my mode number gets very, very high, this group velocity gets very, very small. So what is happening there is actually got a nice intuitive explanation. So let's do this again. Draw this. So remember that if you kind of imagine what's going on inside of this waveguide, you have a wave going down and a wave going up. So just kind of single out one of these waves, and you draw the rays doing this sort of thing, right? So it's going at the speed of light, say, in these directions and bouncing back and forth, but the time it takes to go from, say, here to here is going to be less than the speed of light because it has to travel through this triangle in order to get there. And in fact, as my transverse wave number gets greater and greater as it moves up, then you might get greater and greater steepness. So your group velocity actually approaches 0 as you approach cutoff, because eventually you reach a point where it's completely vertical and the wave just wants to bounce up and down, and there's nothing to propagate it down the waveguide. So that's what's going on with the group velocity. If I were to perturb the signal, the higher the wave number, the slower it will propagate until you hit cutoff, and then nothing can propagate at all. So that's a nice sort of intuitive picture to go with this system here. So we learned that the phase velocity, remember, phase velocity, what did that satisfy? That was omega over beta sub n. That could be greater than or equal to the speed of light, but it's kind of an illusion. It's not a real thing that carries real information. It's just kind of a mathematical quirk derived from the superposition of these waves and their peaks and their troughs. The group velocity is the thing that will carry real information, that if I perturb this and try and send a signal down the line, it will propagate at less than the speed of light. And in fact, as I go higher and higher in mode number, it will go slower and slower. Okay, so that is the distinction between phase velocity and group velocity.